Greetings to the respected faculty. I am Lasya Mandapati from CSC AI and ML section. My roll number is 24951A6686. And today I'll be presenting my project titled Identifying at-risk students using data. This project uses data analytics and machine learning techniques to predict which students are likely to underperform or face academic risk. In this presentation, I'll walk you through the background, the motivation behind the project, the methodology I followed, the Python implementation, and finally, the results and conclusions drawn from the study. In today's education system, a lot of valuable data about students can be gathered, such as attendance, participation, and marks, but it often goes unused. The goal of this project is to convert that data into actionable insights. Using machine learning, predictive model can be built that identify students who are at risk of academic failure. Two algorithms can be implemented, namely the logistic regression and random forest. Not only that, but they can also be analyzed by their performance using metrics like accuracy, precision, recall, and F1 score. The final results show that machine learning can achieve high accuracy in identifying at-risk students, which can help institutions intervene early and improve student outcomes. Educational institutions often face challenges in identifying struggling students before it's far too late. Traditional monitoring methods rely heavily on teacher observations, which can be subjective and time consuming. This project, however, aims to address that issue by building an automated, data driven prediction system. By analyzing patterns in attendance, marks, and behavior, the model predicts which students might be at risk. This allows educators to provide timely intervention as well as support. The main objective of this project is quite clear. First, to develop a machine learning based predictive model to classify students as at risk or not at risk. Second, to analyze which factors, such as internal marks, study habits, or attendance, contribute most to academic success. Third, to compare the performance of the two algorithms and determine which one performs better. And finally, to provide interpretable results that educators can easily understand and act on. In literature review, I studied both traditional and modern approaches. For example, in earlier research, such as by Tinto and Goldstein, they emphasize that attendance and continuous engagement are key indicators of student success. However, with the rise of data science, researchers like Romero, Ventura, and Hussein applied machine learning algorithms to predict academic performance. Their studies show that models like random forest and decision trees can outperform basic statistical methods. This project builds upon those findings by applying supervised learning techniques to educational data, combining accuracy with interpretability. For this project, a simulated dataset containing 10 student records was created, as you can see in the picture here. The attributes also include attendance percentage, internal marks, study hours, and participation in class activities. The target variable, which is at risk, indicates whether a student is likely to struggle academically. In this dataset, around 7 students were identified as at risk and 30 as not and 3 as not at risk, which we can compute as 70% being at risk and 30 as not. Even though the dataset is simulated, it accurately reflects common academic patterns observed in real classrooms. such as low attendance or poor marks, often correlating in lower performances. The methodology follows a clear pipeline. First, the data is generated and reprocessed to ensure it's clean and ready for testing. Then, it's split into training and testing sets in an 80-20 ratio. Two supervised learning algorithms were used: logistic regression for interpretability and random forest for accuracy. Both models were trained using scikit-learn in Python, and the performance was evaluated using standard metrics. Finally, a feature importance graph was plotted to identify which attributes had the strongest influence on the predictions. The implementation was done entirely in Python using libraries like Panda, NumPy, C1, scikit-learn, and Matplotlib. The program first generates synthetic student data. It then trains both models and displays results directly in the console. I used Google Colab to run the code because it supports scikit-learn and provides built-in visualization support. This setup allowed me to execute the entire pipeline without needing an external dataset or database connection. The code also prints the dataset accuracy results and a bar chart which shows features showing which features are mostly important in predicting academic risks. After training both the models, here are the results. The logistic regression model achieved an accuracy of 90% with an F1 score of 0.94, as you can see here, and a precision of 0.89, meaning it performed well overall and captured most at risk students accurately. The random forest classifier, however, achieved perfect accuracy, precision, recall, and F1 score, which means it correctly classified all students as either at risk or not at risk. This shows that ensemble methods like random forest can handle complex feature relationships better than linear models. These are the results of the code and the sample used before. And as you can see, it is 100% accurate and precise. This slide shows the feature importance graph generated from the random forest model. It highlights which feature influences the predictions most. And as you can see, attendance, internal marks, and student hours have quite a bit of influence. Study hours contribute moderately, while participation plays a smaller role but still a measurable impact. This confirms that students with consistent attendance and strong internal performance are likely to be less likely to be at risk, which aligns perfectly with the education theory. From these results, several key observations can be made. First, both models were highly effective in identifying at risk students, showing that even small data sets can provide meaningful insights when properly analyzed. Second, logistic regression provided transparency, showing why students were predicted as at risk, while random forest provided superior accuracy. This balance between accuracy and interpretability is crucial in real world education, where students need not just predictions but explanations as well. Overall, the project demonstrates that machine learning can make academic monitoring more efficient, consistent, and data driven. In conclusion, this project successfully developed a predictive model for identifying at risk students using data analytics and machine learning. It proved that attendance and internal marks are critical indicators of academic performance and that models like random forest can achieve near perfect accuracy. For future, this project can be extended in several ways by using real institutional data, adding behavior or online learning indicators, testing advanced algorithms like neural networks, and also by developing a dashboard that alerts teachers about students needing attention. Ultimately, the goal is to create smarter, data driven classrooms that promote early intervention and improve student success. Thank you for listening. I hope this presentation showed how data analytics can make a real difference in education.